A more advanced differential equation that we could look at is something called logistics growth. And so exponential growth happens when you have growth without bound. So if you have a bacteria, later there's two bacteria, and then it doubles, and then doubles again, 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 and again. But as you notice, these bacteria do have a limit, and that is the fact that they can't grow outside the area of the screen. Okay, and so logistics growth comes in when there are limits placed on, not like mathematical limits, but like physical limits placed on the growth. And these could be anything such as a physical space. So if you have bacteria, you have a petri dish that they can't outgrow. If you have deer in a forest, there is the element of food. Like if there's not enough food, then the ecosystem can't support that population. Same thing with rabbits, or really any competition for resources. You can think about people on the planet. Right now we have 7 billion people or so, but we're going to run out of resources eventually, and we cannot continue to sustain exponential growth. So we have a logistics growth equation, and it basically takes into the idea that there is a carrying capacity. There is some maximum amount of population that the system can sustain. And so we say in words that the rate of change of population with respect to time is directly proportional to, so the same idea that we're setting up exponential growth, it's directly proportional to both p and the difference between the carrying capacity, we'll call it n, between n, the carrying capacity, and the current population, p. So this is our words for logistics growth. Let's put this into math because it's a nice formula. And so we have the rate of change of p with respect to t is directly proportional to the population and the difference between the carrying capacity and the current population. This is logistics growth. N and K are both constants, so just be aware of that. They're usually numbers. And this is what the formula for logistics growth looks like. If we were to graph a slope field for this, there are two main characteristics. The first is that the population has no growth when p equals 0. And so here's p equals 0. So the slope field would look like this. Here's the time axis. Here's the population axis, like that. And then as the population gets bigger, like we have some growth, more growth, and so it looks exponential, like this, pretty high growth. But then the other place where the population has no growth is when p equals the carrying capacity. Notice that if you plug n into this equation, you'll get 0. And so at n, there is another flat line on the population slope field. And so what happens is that these start to taper off and go back to a slope of 0, like this. And so a solution curve to this would look something like this. You would start off with some initial population. It would grow exponentially. But then competition for resources, you're running out of deer food, or, your bacteria are encroaching upon the edge of your screen. But essentially the population will level off and then maintain steady at the carrying capacity. The rest of the slope field, if you started a population that's too high, let's say you start with too many deer in your forest, what will happen is that the deer will just start dying off, and you'll eventually just go down to too low. You'll just die off to the carrying capacity in a more mathematical sense. There's no growth at all because you can't sustain that population. So this is what logistics growth looks like. Let's take a look at a question that might be asked related to this. Oh, that's kind of weird. So dp dt equals 5p times 1 minus p over 300. The first question is, does this look like logistics growth? If you answered yes, it's true because, this is the logistics growth video. And check it out, you have a p on the inside, or on the outside of these parentheses, and you have something minus p on the inside of these parentheses. So you do have this logistics growth relationship. The question here is, what is the carrying capacity? The easiest way to answer this is not to do any math. Don't try to make, it's not 1, that's not the carrying capacity. The easiest way to do this is to ask the question, when does dp dt equal 0? Because dp dt will always equal 0 at the carrying capacity. So let's figure it out. If we take 5p times 1 minus p over 300 and set it equal to 0, clearly p equals 0 is a solution. And then we can set 1 minus p over 300 equal to 0. So we get p over 300 equals 1, and so p equals 300. This is the other place where the slope, the growth rate for the population is 0. Guess what? That's our n. N is 300, and that's your carrying capacity. And that's basically it to find that. So you'll see questions like this pop up every now and then, but it's good to recognize that, hey, it's not always going to be this number. You might have to do some algebra with the rest of it inside to figure out what the carrying capacity is. Hopefully you enjoyed this. Great.